We would now like to consider in a systematic way the physical properties of organic molecules. By physical properties, I am referring to the following 5 properties: boiling point, melting point, polarity, solubility, and density. Okay, so these properties affect how a molecule behaves when you have a bunch of it. And this topic is going to be reinforced by working with these molecules in the laboratory, but what I hope to present here are some basic principles. The question we want to be able to answer is, can we make any predictions about any of these properties based on the structure of the molecules? And if I'm going through this lesson with you, the answer is obviously going to be yes. So let's dive in and get started. We're going to start by talking about boiling point and melting point. And much of our discussion will apply to both of these properties, but we'll have a few extra things to say about melting point that do not apply to boiling point. So what the boiling point specifically depends on is the molecule size and the strength of the intermolecular attractive forces. Okay, so what it means for something to boil is to go from the liquid phase into the gas phase. An analogy that I like to use about gas phase molecules is that they can go wherever they want. Okay? A gas, as you know, is molecules that fill the room completely. So I like to think of gas phase molecules as being like single people. They can just get in the car and drive wherever they want, whenever they want, don't have to answer to anybody. Whereas molecules in the liquid phase are more closely attached to other molecules. I think of liquids as being like married couples in which you have to at least talk to somebody else before you get in the car and go someplace. Whereas solids are molecules that can't go anywhere, and I like to think of solids as being families with small children, because if they get in the car to go someplace, the most common response out of somebody being strapped into their car seat is, wah! And start crying, so you can't go anywhere. At least that was true when I had a small child. Okay, so let's look at some boiling point data for alkanes. Okay, so we're going to look at pentane, hexane, heptane, and octane. Pentane has a boiling point of 36, hexane 69, heptane 98, and octane 126. So as you can see, bigger molecules have higher boiling points, and the reason is because it's more difficult to get them into the gas phase, and each carbon adds about 30 degrees to the boiling point. Okay, so that's what the data is showing us. Okay, but size is not all there is to it. Let's consider the following boiling point data. We're going to have pentane on this list again, still 36, but I'm going to add 2 other molecules, butyraldehyde, the 4-carbon aldehyde, and butanol, the 4-carbon alcohol. Well, what matters about these molecules is not how many carbons they have, but how many non-hydrogen atoms they have. In one case, one of them has an in both of these 2 cases, they have oxygens. In one case, we have a carbon-oxygen double bond. In the other case, we have an alcohol. But they all have 5 non-hydrogen atoms, so we make the approximation that they are the same size. But their boiling points are vastly different. Pentane's 36, butyraldehyde is about 40 degrees higher at 76, and butanol is about 40 degrees higher yet at 118. Well, the difference, as you probably could have guessed, is due to intermolecular interactions. So let's look at these in a more systematic way. The strongest intermolecular interactions are what we call hydrogen bonds. This is a concept that you may already be somewhat familiar with, but hydrogen bonds are non-covalent bonds. I put bonds in quotes because, as we're going to see, they're much, much weaker than a typical chemical bond, between OH and NH hydrogen atoms and oxygen or nitrogen atoms on adjacent molecules. So this is best demonstrated by looking at the hydrogen bonding in water. So you can see that what's in dashes is the hydrogen bond. So it's these interactions between the lone pairs on one oxygen of one water molecule and the hydrogens on a different water molecule. Well, what's going on? Lone pairs have extra electron density that they would like to share. Hydrogens are less electronegative and they don't have lone pairs around them. So they are happy to take up some of the electron density that the oxygen lone pair wants to share. Okay, so the molecule that has the lone pair on oxygen that it's willing to share is called the hydrogen bond acceptor. The molecule with the hydrogen is called the hydrogen bond donor. Okay, so in the hydrogen bond donor molecule, the oxygen is more electronegative than the hydrogen. Therefore, that OH bond is polarized towards the oxygen, leaving the hydrogen more electron deficient and willing to accept electrons from the lone pair of an oxygen on an adjacent molecule. Okay, hydrogen bonds may be the strongest intermolecular forces, but a hydrogen bond in water typically has a strength of about 5 kilocalories per mole, and a covalent bond is more on the order of 100 kilocalories per mole. So hydrogen bonds are still about 20 times weaker than a covalent bond. The second intermolecular attractive force that is even weaker than hydrogen bonds are what we call dipole-dipole interactions. Okay, so a molecule that has dipole-dipole interactions would be acetone. And if you look at its structure, it's got a carbon-oxygen double bond. And this molecule, like water, but it also has a permanent dipole. And recall the dipole symbol, the arrow is pointing towards the negative end of the dipole, and the place where the two lines cross that looks kind of like a plus sign is pointing towards the positive end of the dipole. Okay, so this molecule has a permanent dipole pointing upwards. Well, what a dipole-dipole interaction is when molecules with net dipoles, such as this, line up such that their positive ends and negative ends are opposite. So we could take another acetone molecule, line it up like that, with its dipole pointing in the opposite direction, and that gives rise to an electrostatic attraction. Okay, the positive end of the left-hand molecule is on the bottom, the negative end of the right-hand molecule is on the bottom, and the positives and negatives attract on the bottom. And then similarly on the top, we have a negative end on the left-hand molecule, a positive end on the right-hand molecule, and they are attracted to each other. The third type of intermolecular force, which is even weaker, are what we call van der Waals forces, which some people also call London dispersion forces. That's not after London the city, that's after Fritz London, who was a physical chemist who actually postulated the existence of such forces. So what van der Waals forces are that temporary dipoles can form even in nonpolar molecules. Well, to have a dipole-dipole interaction, you have to have a permanent net dipole, and the molecule has to be polar, which means it has to have polar bonds. But in nonpolar molecules, so such as hydrocarbons, where there are just carbon-hydrogen bonds, which we consider to be nonpolar bonds, you still have occasional temporary dipoles. And the way we explain this is that electrons are always moving kind of randomly in their quantum mechanical sense through the molecule. They don't stay completely localized in one place. So sometimes there may be a little more electron density on one end of the molecule, and as a result there's got to be a little less electron density on the other end of the molecule because the total electron density has to be the same. Well, if you have one molecule that temporarily is negative on one side and another molecule that is temporarily positive on one side, those ends will attract each other. These are short-lived interactions. They're very weak, but they are important because they explain why nonpolar molecules are not all gases. Why is hexane a liquid and not a gas? The only explanation we can come up with is van der Waals forces. Okay, so let's look back at the boiling point data, and I'm going to add one more column to this table. Okay, so pentane, butyraldehyde, and butanol once again. In pentane, the strongest intermolecular force is van der Waals forces. That's not a very strong interaction, so as a result, it's very easy to get this molecule into the gas phase, and it has a relatively low boiling point at 36 degrees. In butyraldehyde, we have the carbonyl group, we have the carbon-oxygen double bond, and that allows us to have dipole-dipole interactions like we saw with acetone at the top of this slide. The existence of the dipole-dipole interaction being stronger makes it more difficult to get the molecule into the gas phase. You have to break that stronger dipole-dipole interaction to get the liquid molecule separated and into the gas phase. So therefore, you have to heat this molecule up to 76 degrees before it's going to boil. And then finally, butanol, being an alcohol, has hydrogen bonds just like water does. And since the hydrogen bonds are the strongest of all, you have to heat butanol even more to break those hydrogen bonds and get it into the gas phase. And that's why its boiling point is 118 degrees, 40 degrees higher